Okay, so we have defined electric potential energy, electric potential, which is the electrical potential energy divided by the task charge. Right? So that's the definition of the electric potential, or more precisely, the electric potential difference between 2 points in an electric field. Right? And the point is this, right? So we have to shift the focus to the electric potential. It's pretty much like once we define electric field as the electric force divided by the task charge, we have shifted our focus on electric field. Then we spend a lot of time finding the theory to calculate electric field, and then did a lot of practice. And then we did the same thing, right? So we want to find a fundamental theory to calculate the electric potential from any electric field, any kind of electric field, okay? We started with the simplest one, okay? We started with the simplest one, a uniform electric field. For a uniform electric field, we found out that it's actually very easy, okay? So the conclusion is this: if there are 2 points in a uniform electric field, the potential difference between them, okay, you can only calculate the potential difference between them, right? Because you need to set a reference point if you want to calculate the actual value of the electric potential at a specific point. This equation helps you to find the difference, potential difference between 2 points, and it's always going to be the electric field. And because it's a uniform, so this is going to be a constant, times the distance between these 2 points in the direction of the electric field. Okay, so you can think of the electric field as in x direction, and then you just need to multiply electric field and the displacement, the x component of that displacement. Okay, but remember, when you use this equation, you only know the value of the displacement, the difference, right? You can't find out the which one is larger, which one is smaller, the potential at these 2 points, right? But as I said, there's a general conclusion, which is always true in electric field. The direction of the electric field is always the direction of decreasing potential, right? So you use the direction of the potential, direction of the electric field lines to determine VB or VA, or VA is higher, right? Then you know that I should write VB minus VA equals that number, or VA minus VB equals that number. That's what we learned. And we also did a practice example last time, right? So now, once we have found this electric potential, calculate the theory to calculate the potential difference between any 2 points in a uniform electric field, okay? We should be able to calculate the potential energy difference, right? So I can go ahead and multiply this by Q naught, so I can calculate the potential energy difference between any 2 points if there's a task charge moving in that electric field, okay? And then once you can calculate the difference in the potential energy, and then this object, this charged object is moving in that electric field, so I can apply conservation of energy in the process, right? So these 2 points, I would just pick them as the initial and final points, right? And then I can still use conservation of energy to make predictions, okay? So that's what we're gonna do next, okay? So conservation of energy, we already learned that in physics 1. It's a very intuitive law, okay? Energy can neither be created nor destroyed, okay? It can only be transformed from one form to another, or transfer from one system to another system, right? So the notation we used in physics 1, if I would write it in a mathematical equation, that's how I would write it, right? The change in the total energy area in a closed system is going to be equal to the energy transferred into or out of the system by some mechanism, right? So in this class, okay, we're going to only discuss kinetic energy and electric potential energy on the left-hand side. So we're not going to worry about other forms of energy in this class, only kinetic energy and electric potential energy. Now the only method to transfer energy we're going to consider in this class is still going to be work, okay? So that's going to be the equation we're going to use in this class, okay, if I want to apply conservation of energy in a problem, okay, then how do I use this equation? Well, kinetic energy has a definition, right? It's still 1/2 mv squared, right? So it's true for any object, right? Even if a proton, electron, in atomic or subatomic scale, that's a definition, right? That's always true. So there's nothing changed for this guy, okay? Then if you want to calculate, don't forget the change, right? Whenever you see this little triangle, that's delta. That's a change. So you're gonna pick 2 points, you call them final and initial. Use this definition to calculate final minus initial, right? So that's the same we did in physics 1. Now the delta UE, you would calculate use the definition of the potential. So I'm going to rearrange that, and then that's how I would calculate the potential energy of a test charge moving in this electric field, right? So again, so this test charge is not going to change, right? It's like the mass, it's a problem. So what changes is going to be the potential, right? So you see that if you can find the final and initial potential, this big V, okay, then you can set up this equation, okay, and of course work is still the same definition, right? Work is going to be force times displacement times cosine theta. Okay, so this and this, the definition doesn't change, right? This is a new thing we define here, electric potential energy. Then we can set up conservation of energy to solve any problem, right? If something is moving in a charged object, it's moving in an electric field, okay? And then of course, when we put a subscript ext here, that means you only consider the work from the outside, right? So work done from external force. And as I said in physics 1, if you define a potential energy associated with a conservative force, you already include the force in your system, okay? You already did that. So it's not external force. It's not external force anymore, okay? So you don't consider it external force. So that means, so remember what we did is that we included gravitational potential energy on the left. So we never calculate the work done by gravity on the right, because gravitational force, it's already an internal force in my system once I define gravitational potential energy. So the same deal here. We have defined electric potential energy. So that means if you see electric force on this object, of course if it's a charged object and moving in the electric field, there will be an electric force on it. But this electric force is going to be considered inside our system, right? We already include that in our system by defining the electric potential energy, okay? So you don't calculate work done by electric force on the right because it's not an external force, okay? It's already including our system whenever we define a potential energy associated with this conservative force, right? All right. So and then pretty much the same. The steps are still the same, right? You set up this equation, you rearrange them. Okay, you can find things you need. Okay. So now let's take a look at an example. So this is still the example we saw last time, right? Parallel plates, set up the electric field, and then we're going to release a proton and electron in the middle, okay? Proton is going to move to the negative plate, electron is going to move to the right plate. So let's see what we want. And we found the potential energy of these two guys last time, right? When they reach the plate. Now we want to find the first part. What is the proton speed when it collides with the left plate, okay? So let's see. These are still these two plates. This is negative plate, positive plate. Okay, a proton released in the middle. It's going to definitely feel a force to the left, right? Because the field is to the left. So this guy is positive, so it feels the force in the same direction as the electric field, right? So it's going to definitely be moving to the left plate, and then faster and faster because there's an acceleration. It has an acceleration. So we want to find the speed of this guy when it reaches the plate, okay, the left plate. We can solve this problem using kinematic equations, right? Because this is uniform electric field. So everything is a constant, force is constant, acceleration is constant, right? So you can't solve this problem using kinematic equations and Newton's laws, okay? But we want to practice this conservation of energy, okay? And we're going to see that if the electric field is not uniform, then you cannot use kinematic equations and Newton's law. You would have to use conservation of energy, right? So we want to use this problem to practice conservation of energy in a simple case, okay? Okay, so I decide to use this conservation of energy. I'm going to write it down. Okay, and the conservation laws are my favorite laws, okay, because it's very easy to set them up. You always set them up the same way. You will have many terms, okay, but you always set them up the same way. Okay, I don't even need to use any detail from the problem. I know that this is going to be how I set up data K, right, final minus initial, and then the data UE, it's going to be this charge. So this is a proton moving, it has charge, so I'm going to have QV final minus QV initial, right? No absolute value sign, right? Because the definition of the potential and potential energy, no absolute value sign, you don't make anything positive, you don't. Now, external work. So you're going to count the work down from the outside, right? The electric force, as I said, we already included in our system by defining electric potential energy. So this force is not from the outside anymore, right? So, and that's the only force on it. So there's no force, okay, no external force on this proton. So I'm going to put a 0 on the right hand side, right? And don't even need to calculate the right hand. Now let's see. I want to find out this V final, right? So the V initial, it's released from rest, okay, nice, okay. So I get a 0 here, V initial is 0 for the proton. Now the charge is going to be this, positive, right? So that's the charge of the proton. Now these two potentials, right? The problem already says that let's assume the potential of the midpoint is 0, right? That's what we used as the reference point last time. So the big V different than little v, okay? It's just the potential at the middle point, right? Because that's the initial point of the motion. That's going to be 0. And then final potential is the potential we calculated of the left plate, right? It's going to reach the left plate, okay? And what was the number we calculate? This is going to be negative 2000 volts, right? That's what we calculate. Now you see that I do have all the numbers I need, right? I just plug them in and then rearrange this equation. Of course, I need the mass of the proton. All right? So once now you can pause the video, plug numbers in, and then rearrange this equation to find the final velocity of the proton, okay? All right, let's see. So at the end, so first of all, let's rearrange this equation. This is going to become 0, so I'm going to get this. And then I can move these two terms to the right, so I would get negative QVF plus QVI. Right? And then divide both sides by 1/2 m and then square root. That's going to be VF. Right? So I will have 1/2 m here, negative QVF plus QVI. This whole thing square root. Okay? So then you can plug numbers in, right? So for the proton, the number I got is okay. So because the charge is going to be this number positive, these two potentials are here, Okay, so then that's how we find the final velocity of the proton, right? Exactly the same as physics 1, right? The only difference is that now we're using a different potential energy, electric potential energy, right? Instead of gravitational potential energy or elastic potential energy. Now let's take a look at the next part. Okay, what about the electron, right? If there's also an electron released at the middle point, and then of course it's going to move to the right because it's going to feel a force opposite to the field. That's negative charge, right? So it's going to move to the right plate, get faster and faster, okay, and then it's going to reach the right plate. So we still want to find the velocity of this electron when it reaches the right plate. Okay, I'm going to set up the same way, right? Set up the same way. You see that delta k plus delta u equals this. No change, right? No change. These four terms, they never change, right? Because that's the definition. Now, okay, the electron still has a one force on it. We can ignore the gravity of this proton electron, right? Because they are atomic, they are elementary particles. Gravity is much, much smaller compared to electric forces. So I will still have this. I will still have this, right? You see that nothing has changed, right? This is going to still be the same expression I got at the end, right? So the only difference is going to be this, okay? The charge you plug in is going to be negative number, right? Because the charge of an electron is negative number. So the charge you plug in is going to be negative E in this case, okay, for an electron. So keep the negative sign, all right? Now the electron has a mass. You also need the mass, the constant. Now the final initial potential is still the middle point. Okay, so that's still 0 in this problem. Now the final point is going to be the right plate. So what is the potential of the right plate? We also calculated last time. This is 2000 volts. Okay, so you're gonna plug all the numbers in with all the signs, okay? Don't throw away negative signs, okay? And then if you have done the math carefully, okay, pause the video, do the math. The final answer for the electron the final velocity is gonna be 2.65 times 10 to the 7th meters per second. All right, so that's the speed of the proton or electron. Okay, so conservation of energy. You see that we're still using a lot of laws, theories, and skills we learned in physics 1. Okay, that's why you need to take physics 1 before this class. All right, so we have done that. Now we're going to move on to slide PowerPoint 6. Okay. Remember the theory we just calculated, we just found was only for uniform electric field, right? Don't forget what we're doing here. We have defined electric potential energy and electric potential, and then we shift our focus on this guy, because once I have a theory to calculate the potential, then I can find the potential energy very easily. Then I can do use energy method to predict the motion, study the behavior of these elementary particles, right? So that's why we have been focusing on the potential. We found a theory for the potential, but this is only for uniform electric field, right? This is a very easy one, but this is not a general conclusion for any electric field, right? This is very limited. You can only use that for electric field, uniform electric field. But we want to use it to as an example, okay? To find this. Use this definition of a potential to find the expression for the potential and potential difference in a simple case, and also apply conservation of energy. That was the purpose. Now we're going to find a general theory for any kind of electric field. So that's what we're going to do next. Okay. Remember, for electric field, what did we do? Well, we just went ahead to use a point charge to find the electric field, the theory for a single point charge, and then we generalize it to any combination of point charges or continuous charge distribution. That's what we did, right? So now we're going to do the same thing. We're going to start from a single point charge, and then we're going to use a fundamental theory to derive the theory for a single point charge, how to calculate potential for a single point charge. And then we're going to generalize it to a group combination of many charges and also continuous charge distribution. All right, so let's take a look at the first slide. Now I'm going to start with the simplest case, right? Positive point charge. Okay, so this guy, the electric field I draw is going to be like this, right? Away from it, radially outward. Now let's pick 2 points, and then I want to find use the definition of this potential to find expression for that guy. That's my goal. Okay. So let's see. So let's pick 2 points, okay, like A and B, or any 2 points, okay? So I'm going to use that theory to find out the expression. So in order to do that, so let's use this theory, E dot dr, okay? Now this E, remember, we do have an expression for this guy, okay? We derived it for a point charge. There is a complete equation, which is Ke q over r squared times r hat, okay? You can find this complete equation in one of the slides. We never use it that way because when we use this theory, well, we just first calculate the magnitude, right? Put an absolute sign here, so the magnitude of the electric field is going to be K E q over r squared, and the direction we know that, okay, it's going to be outward if it's a positive source, negative inward it's going to be a negative source. Now we're going to do some math here. We're going to do this vector analysis, vector integral. So I'm going to use this complete expression. So I will get Ke q over r squared r hat dot dr. Okay, so this guy is just going to give me, okay, so Ke, you can take it out, right? And then this Q, remember this Q is the source charge, so you can also take it out. So you will have from A to B, now you still have 1 over r squared, okay? This guy, okay, so that's a nice thing. If you multiply the displacement, remember this is a displacement from A to B, with the unit vector in the radial direction, you actually just get the dr. The magnitude of this displacement in this radial direction, okay? And that is very nice because you see that once you have that, you're gonna just look it up in an integral table, right? So you would just have delta V equals V minus VA, negative Ke Q, right? Then from RA to RB, dr over r squared, right? And this is very easy to find, okay? This is just going to be, if you look it up in the integral table, this is just going to give you a negative 1 over r, and then bounds from RA to RB. And you put it in, well, this negative sign is going to cancel that negative sign, right? At the end, what do you get? You're just going to get Ke, you plug this bounds in, 1 over RB minus 1 over RA. So you will just get Ke Q over RB minus Ke Q over RA. So this is our conclusion, right? So if there is a point charge and then it creates electric field around it, right? So you will always have this conclusion, okay? You pick any 2 points, so they don't even need to be on the same electric field lines, okay? Say you pick A, you can generalize it, and then B here, okay? So all you need to do, if you want to find the potential difference between these 2 points, you just do KE Q over RB minus KE Q over RA. That's a conclusion from the expression from the electric field we derived for point charge. So it's still a conclusion from Coulomb's law, right? Pretty much everything is derived from Coulomb's law. Now you can see this RA and RB is just the radial distance between this point charge to the point you want to evaluate. So in this case, this is going to be RA, and this is going to be RB. So they're going to be 2 numbers, right? So you plug them in, okay? So in this case, for a point charge, we usually pick a reference point, okay? We usually pick the infinity as a 0 reference, okay? So in that case, the potential of any point is just going to be KE Q over R, right? So you see that if you apply this equation for point B, you get this term. You apply this equation at point A, you get this term. You subtract that. That agrees with this theory we just derived, right? So for point charge, the electric potential created by point charge, okay? So the 0 reference we pick is always going to be infinity, right? And that makes sense, right? See that V infinity is going to be KE Q over infinity. That's going to be 0, right? Okay, so that's a good reference point. Okay, so we always pick that reference point, okay, at infinity. So the potential you calculate is going to be the actual value of the potential at any point, right? So you don't need to specify a 0 reference, because like everyone is going to pick the same 0 reference, okay? So that's going to be a theory, okay? So that's our theory for a point charge. We're just going to go ahead and use this theory. So for uniform electric field is this theory, but that's the simplest case, right? And what we just derived is that for a point charge, single point charge, the potential at any point in this electric field created by this point charge, it's going to be this equation. And notice that there's no square down here. It's a little bit similar to this equation, but there's no square down here. There's no absolute value sign here, no absolute value sign. Okay? So that the potential can be positive or negative. Okay? And then think about it. If you have a negative charge, so you would draw the electric field lines this way, right? If we assume infinity is 0, right? So say this is infinity. Okay, really far away. Remember, in the direction of the field line, electric field lines, potential always decreases, right? So if this is infinity, the potential is 0, and then these lines are toward the negative charge. So that means any point you pick here should be lower than 0, right? As I said, this is a general conclusion. In the direction of the electric field, potential always decreases. So of course, the potential you calculate for a negative source charge is going to be negative everywhere. It is negative everywhere, right? This is going to be a positive number. This is going to be a positive number. But if the source charge is negative, this is going to be a negative number. Okay, everything is consistent in physics. Everything is consistent in physics. So you just need to stick to the laws, stick to the definitions. Don't make your own definitions. Don't make your own laws, your own theories. Okay, isn't it nice? Okay, in physics. Okay, you don't need to use your own judgment. Okay, you do the math. The math is going to tell you all the answers, positive or negative. Then it's positive or negative. Okay. So, but this, remember, what is this sequence? This is the electric field created by point charge. That's the magnitude. That's why we have an absolute value sign here, because magnitude of vector has to be positive. right? There's no negative magnitude in this word, right? So that's why we have the, you're going to remove the negative sign, right? Because this is the theory, okay? Just use this theory, okay? All right, so that's the theory we derived for the point charge, okay? So then you see that that's similar to that theory. So if I have a group of charges, I want to find the potential at any point in this net electric field created by a group of charges. I just use that theory, right? And then I'm just gonna use superposition principle. And if you use superposition principle for potentials, it's much easier than electric field, because remember, if I have like Q1, Q2, Q3, let's just use 3, and I want to find the electric field at this point. How do I do that? Well, you're going to draw arrows, because the electric field is a vector. This guy, electric field away from it, E1. This guy toward it, electric field E2. This guy positive away from it, right? E3. And then you're going to add these 3 vectors, okay? So you're going to do vector analysis. That's how we're going to find the, if I say find the net electric field at this point, okay? You're going to do E net equals E1 plus E2 plus E3. Right? If you still have these 3 charges, and I want you to find the potential at that same point, okay? I still have Q1 here, Q2 here, and then Q3 here. Find the potential at this point, because there's an electric field, still an electric field here. But now I'm not interested in the strength of the electric field, the vector electric field at any point. I'm only interested in the potential at any point. I want you to map out the potential for me. How do I calculate the potential at this point? This guy has a potential, right? Creates a potential here, V1, which is going to be KE Q1 over R1, right? So of course this is going to be R1, Q1. What is the direction of this V1? How do I draw this V1? You don't draw this V1. V1 is a scalar. You don't draw arrows for scalar. It's a number here, okay? It's a number here. So then once you have done this, you are done. You don't need to draw arrows. You don't need to break into X and Y components, right? You do the same thing for Q2. Q2 is going to have a potential here, produce a potential here. Use this R2 distance. Use the charge of Q2, keep the sign, and divide them, then you get a V2, a number here. That's it. No arrow, no XY components. You get a number, okay? You do the same thing for V3. You're going to use this distance, VR3. You're going to use the charge Q3. You put them in, you get the number. That's it. You don't draw any arrows. What is the net potential at this point, okay? You add all these V's together. Literally, you add them together. Isn't it nice, right? And then that's it. We're done. There's no direction involved. There's no vector. There's no XY component. There's no arrow, okay? As I said, this is one of the reasons we wanted to introduce potential and potential energy. Working with potential and potential energy is so much easier than working with the electric field and electric force, right? Because they are scalars. They're just numbers, right? If you do things in the energy method, it's a lot easier than using the electric field and force, okay? So that's going to be the superposition principle for net potential due to a group of point charges, right? You just use this theory to calculate the potential due to each point charge, a number, no arrow, okay? And literally add all these numbers together with their signs, so you don't make it positive, negative, positive, right? They will have sign. So even the net potential you get can be negative, okay? All right? And then of course, when you have a group of charges, right? So this is what you do when you have a group of charges, right? So you just calculate the potential from each charge, due to each charge, add them together. when you have a continuous distribution of charge, this becomes integral. So this is going to be the hard part, right? So we're going to do this later, but now let's take a look at an example with a group of point charges. So that's the question on slide 4. Let's take a look at it. Take a look at the image, right? Does it look familiar to you, right? We actually did this, right? We actually saw these 3 guys in electric field, okay? If you still remember, or you can check the PowerPoint. We have these 3 guys here. 5 nanocoulomb at the origin, and then 6 nanocoulombs on the x-axis, and then -3 nanocoulomb charge on this y-axis, negative y-axis, and this is a 0.1 meter, okay? This is 0.3 meters, okay? Remember what we did with these 3 guys in the electric field part. We wanted to find the force on this guy, right? And then how do I find the force on this guy using electric field? We remove this guy first, and then calculate the electric field created by this guy. So that's going to be a positive away from it, right? Remember what we did, okay? Is it coming back? Okay. We found the electric field created by this negative nanocoulomb charge. Negative, so it's down, right? So, and then we found the net electric field by combining these 2 components, because they're already in x and y, so I don't need to break them. So that's the net electric field. And once you have the net electric field, you can put the test charge back, because now you're just going to work with these 3 guys, this test charge, right? So there is an electric field created by these 2 charges at this point. And then now you place a charge, test charge Q naught, 5 nanocoulomb here. What is the force this Q naught feels? Well, you're going to use the theory, this theory. Right? That's what we did in the electric field part. Now we're going to use these 3 charges. We're going to do the potential. Okay? So it's going to be these 3 charges. Okay? Now I'm interested in the potential energy of this 5 nanocoulomb. So I'm going to still do this, okay? I want to calculate the potential energy of this 5 nanocoulomb charge at the origin. I'm going to think of these 2 guys as a source. They create the electric field all around them, okay? True, okay? But now I'm interested in potential and potential energy. I'm not interested in the electric field and electric force, okay? So I'm going to calculate net potential at this point. And once I have the net potential here, I'm going to place the test charge 5 nanocoulomb here, so I can calculate the potential energy by using the relation between the potential energy and the potential, right? So now let's find the potential, net potential created by these 2 guys, right? So all I need to do is just calculate, say, if this is Q1, this is Q2, I would just calculate V1 and V2 and add them together, right? How do I calculate V1? This theory, right? KE Q1 over R1. No square, no absolute value sign. This is Q1, plug in R1, 0.3 meters, right? You get a number. That's it. Don't draw any arrows, right? Don't break it in X and Y. It's a number, it's a scalar. It doesn't have any direction. Now do the same thing for this guy. KE, the same theory, Q2 over R2. Now Q2 is this number, R2 0.1 meters. Put it in, okay? And then keep the signs, no square here. You get a number. Don't draw any arrows. There's no arrows to draw, okay? These are 2 scalars, okay, at this point. And then you add them together, that's going to be the potential. Then that's it. It's still going to be a number. You don't need to tell me a direction. It doesn't have any direction, okay? So that's going to be the first part, right? That's the question on slide 4. Once you have done that, you can go ahead and calculate the energy, the next part, the energy of this Q0, 5 nanocoulomb charge sitting here, feeding the electric field created by these two sources. But again, just multiply them together, right? Keep all the signs. There's no direction. The energy is just going to be a number, okay? Now I can pause the video, finish these 2 parts. All right. Okay, let's see. What are the numbers I got? So the number I got for this guy, right? You put KE, Q1, R1 in, I get 180 volts. Then that's it. No arrows, no direction. You put this number in, this R2 in, right? The number I got negative 270 volts. Negative it is. Don't erase this negative sign. You add them together, what do you get? You get negative 90 volts. Okay, so the potential at this point created by these two sources is negative 90 volts, okay? And you don't need the problem to tell you a zero reference, because when we use this theory, everyone is going to agree that we assume infinity is our zero reference, okay? Which is intuitive, right? Okay, so that's that. And then you see that the next part, once you have done this part, this is the hard part. And then you can move on to the next part. If I want to find the potential energy of this 5 nanocoulomb charge, I would just multiply this test charge by the net potential at this point, right? So multiply them together, right? So the answer I got is going to be negative 4.5 times 10 to the negative 7 joules. Negative it is. Okay, don't throw the negative sign. It's potential energy. Potential energy can be negative. Kinetic energy, no. Kinetic energy is never negative, right? From the definition, right? There's no reason, right? Because we define it that way. 1/2 mv squared. Okay, you don't need to interpret the words, the names, okay, literally, right? What does energy mean, okay? From the meaning, can it be positive, negative? Forget about it, right? Everything has a definition in physics, right? Even if I don't call it energy, this is still 1/2 mv squared, right? And that thing is still Q times V, right? You call them whatever you like. The definition don't change. Definitions don't change. So if they can be positive, negative, then positive and negative, right? You don't erase this sign. All right? So in this case, you see that the nice thing is this. If I replace this guy with a different charge, I keep these two sources, right? I replace this guy with like another charge, like 2 nanocoulomb. What is the potential energy of this guy? Well, multiply them together, right? I replace this guy with negative 7 nanocoulomb charge. What is the potential energy of this guy at this point when it's sitting here? Multiply them together. Okay, so you always get to do this, very easy, right? Once you have done the hard part, calculating the potential, right? Even though this is a hard part, it's a lot easier than working with electric field and forces, right? Because they are scalars, okay? All right? So a nice conclusion, okay, in this part, after this question is this, right? You see that if I call this guy Q3, okay, not Q1, or not Q0. Let's see, excuse me. Let's see what this, if I just write the expression of the energy of 3, right? So that's the potential energy of Q3. I would do Q3 V net, right? And the V net we calculated, it's going to be, now I'm going to use the symbols because I want to draw a general conclusion. KE Q1 R1 plus KE Q2 over R2, right? That's how we got this to the net potential. Now I just use the expression. Now I would get, if I distribute it, Q1 Q3 over R1 plus KE Q2 Q3 over R2. But this R1 is this distance, right? If I call this guy Q3 here, that's just going to be the distance between 1 and 3, right? So I'm going to change the notation. I'm going to call it R13 to see the symmetry here. This distance is the distance between Q2 and Q3. So I'm going to call it R23. Now you see the symmetry. Now see the pattern, right? So if I want to calculate the potential energy of Q3, all I need to do is actually do this, right? I just do KE, QI, QJ, and then the distance between these two charges. And then I'm just going to pair it up with every other charge and then add these numbers together, right? So you can do the same thing for Q2, right? So say I have these three charges here. I want to find the potential energy of Q2. You would just replace everything with Q2, Q1, Q2, Q3, right? R21, R23. And if you want to calculate the potential energy of Q1, you can still do that, right? So you still use that pattern, but you still get two terms. You just pair this guy up with Q2, pair this guy up with Q3, right? You get that. So if you have a system, these three guys, they are a system. And if you want to calculate the potential energy of this system with the group of point charges, all you need to do is just use this expression. Right, and just run it over any pair, right? Just pair them up, okay? But remember, if you have done Q1, Q3, and then you do Q3, Q1, you get the same number, right? So that's a double count. So in order not to double count, we put a restriction here. So whenever you do this, use this expression to calculate the term, make sure that the I is less than J so you don't double count. So this is going to be a general conclusion, right? If I want to calculate the total potential energy, electric potential energy of a system with a group of point charges, okay, what do I do? Well, I'm just going to use this expression, run it over every pair of these charges, but I only do it once with one pair, right? Once I've done Q1 and Q7, I don't do Q7, Q1 again, right? I only do it once. So that's why I put this restriction here, okay? So that's a conclusion we can draw from this problem, okay? All right, I'm gonna stop here for this video.